Alright, so this is the second of our videos on limits for Math 1560 Calc 1 at the University of Lethbridge for fall 2017. In this video we're going to give you a definition for the limit. We're going to introduce some notation, and we're going to cover some of the basic properties that limits satisfy. So here's the definition of a limit that we use in Math 1560. It's a little bit wordy. I'll say a little bit about why we kind of go with this wordy definition. So here's the definition. It says, so we start with the function f, and remember that when we talk about limits, we're talking about values of the function near a certain point. And so if we're interested, in this case, we're interested in values of a function near this point, a. Okay? And so it turns out when you're considering limits, you don't necessarily care about the value of the function at a. So the value f of a doesn't really matter for the limit. What the limit cares about is not the value at that point, but at the values close to that point. And that's why we need to ensure that we can evaluate the function at any point which is sufficiently close to the one that we're interested in. So the function needs to be defined at all real numbers near the point that we care about, and then we say that the function has a limit, and that limit is going to be a number. So in this case we say L. So L is a number here, it's some real number. It's a value, right? So L is like a y value, and we say that the limit equals L if we can make the value of f of x, if we can make the outputs, the y values for our function, if we can make those values as close as we want to this number by choosing a value of x that is sufficiently close to this number a. Okay, so it's basically saying if you squeeze in close enough, bring x close enough to a, the y values are going to get in as close as you want to this number L. It's an okay conceptual definition. It gives you an idea of what's going on with the limit. The problem with this definition, the reason why I call this an informal definition, it's not a definition that you can use to prove anything. And in math, you're always, if you're writing down a definition in math, you're writing down a definition because you want to use that definition to prove some theorems. You want to use those definitions to learn some things about the world around you, about mathematical objects. You want to figure out what sort of logical conclusions you can come to from that definition. Well, there's not really much you can conclude from this definition. It's nice, but it's also useless. So if you want to actually get any work done, there's this formal definition of the limit. I'm not going to bother to write it down or even mention it in the videos. If you care about the formal definition, the one that is actually used to prove theorems, well, there is a section in the textbook on it. You can see section 1.2 in the textbook, and that will go over this formal definition, and you'll probably, if you take a look at it, you'll understand why we don't cover it in Math 1560. It's a fairly technical definition, and the proofs that you write with that definition can be pretty tricky to get the hang of them. This is not a proof course, so we're not going to worry too much about the formal definition or how to use it. If you go on and you take higher level math courses, you'll run into that definition, and you might have to work with it. I'll show you one illustration to kind of give you an idea of how you would use this precise definition. So the precise definition is phrased in terms of numbers delta and epsilon. And so you think of this number epsilon is kind of the error. It's telling you how much tolerance are you allowing in the y values, how close are you requiring somebody to get to a given point. So you can see this number L here, this value L, our limiting value, and we can see this number A. Now this A, I can drag this point if I want. I can move it around on my graph, and I can look at what happens. And so what we can do here is we can say, okay, I'm going to set my limiting value, I figure out I have some way of guessing what I think the limit should be. And how do I figure out what the limit should be? Well, first I say, okay, it doesn't matter how small I make this error, so this epsilon allows me to adjust the error. I can choose an error as small as I want, and if I want to guarantee that my function has the limit I want, all I have to do is show that I can take a corresponding value for this delta. So this delta is kind of telling me what my x range can be. And if I shrink the x range small enough, okay, I can bring those dotted lines inside the error estimate that I've set, right? So if I have a big error, well, I don't need to zoom in quite as close to the x value. I can let delta sit up there. But if I want to shrink my error way down, well, then I'm going to have to drop my delta down and get it really small so that I can fit in the range that I want. If you want to get into the kind of the details of making proper sense of a limit, this is how you make sense of a limit. It's in terms of playing around with these tolerances for both the x and the y values. You set the y tolerance and then you adjust the x tolerance to match. And if you can always do it, if you can always match the y tolerance, no matter how small you set it, if you can always adjust x to fit within that range, then you've got a limit. That's what the precise definition looks like. So the precise definition, it kind of, what it addresses is it addresses a couple of terms that show up in this definition. It addresses this part, the as close as we want, and the sufficiently close. This is not precise language, and so if you want to kind of really make sense of that, you have to go to this complicated definition. We're not going to go anywhere near it, but if you're curious, it's in the book. Now, with that precise definition, you can prove a lot of useful algebraic properties that limits satisfy. I've written some of them down here. Okay, so these sometimes are known as the limit laws, and there's kind of a constant rule. Right, the limit of a constant is a constant. This one is sometimes called the identity rule. If you take the identity function where the output is the same as the input, also known as simply x, f of x equals x, right? Well, what does this one say? This one really is saying as x approaches a, x is going to approach a. This is almost tautological, right? There's really, this is perfectly obvious. I think there's no controversy on these statements. The remaining ones are sort of algebraic properties. They tell you that, for example, the limit of a sum is the sum of the limits. So we could write this if we want as so the limit of f plus g is the limit of f plus the limit of g. And similarly, if you have a constant, you can take the constant outside of the limit. If there's a constant inside the limit, you can pull it out. Okay. Limit of a product is the product of the limits. Limit of a quotient is the quotient of the limits. And there are a few other properties. There's a few more listed in the textbook that have to do with, well, what goes on if you're dealing with, let's say, composition of functions. And when you can and cannot take a limit inside of a composition, so you can often bring limits inside of well-behaved functions, like a power function or a square root function. There are a few more. They don't all fit on this slide, and they're all in the textbook anyway, so you guys can take a look at those there. But with these limit properties, you can very quickly work out limits for some common functions. So for example, if I wanted to calculate the limit for any polynomial function, let's say I want to do the limit as x approaches 2 of something like x squared plus 3x plus 4, something like that. Well, I can use these rules repeatedly. The first thing I could do is say, well, as the sum rule says I could write that as the limit of x squared plus the limit of 3x plus the limit of 4. X squared, of course, we know that x squared is x times x, so for x squared I could use the product rule. I could use number 5 to say, well, that's the limit of x times the limit of x, and I know from rule 2 that as x approaches 2, x approaches 2, so I know that the limit of x is 2, so this should be 2 times 2. The constant rule tells me that this one should be 3 times 2. 4 is a constant, so the first rule tells me what to do with that, and I can work out that this is going to be, well, 2 times 2 plus 3 times 2 plus 4, and I can work out that value, right? So what do I get? I get 14. Notice that that's exactly what you get if you simply plug this value into your polynomial, right? This is an example of a property called continuity, which we're going to be studying in more detail later on. Okay, one graphical example just to finish with. Somebody gives you a graph with a couple of functions. F of x is in blue, g of x is in red, and you from the graph, of course, we can determine values for these functions, and then we could try to use those to work out these other limits. I'm going to leave 1 for a second. Let me start with 2. What can I say about the limit as x approaches 0 of f times g? Well, from the graph, let's see. What can I say about that? I have trouble, right? Because look at the graph of f of x. At 0, it doesn't really have a limit, does it? Because, you know, to have a limit, as x gets close to 0, I have to be getting a well-defined y value. But if x is close to 0 and negative, my y values are close to 1. If x is close to 0 and positive, my y values are close to 0. There is no limiting value because there's no y value I can choose that's simultaneously close to 0 and 1, right? If I wanted to guarantee that my y values were within a quarter, let's say, of some limit, there's nothing that's going to work. So in fact, I can't really say that it's equal to anything. All I can say is that it does not exist. And the same story is going to be true for the fourth one. That also does not exist. Why? Because again, we notice that the limit for f doesn't exist at 2 because we have this break in the graph of the function, right? I can't agree on what the y value should be as I get close to 2, right? Notice that in these limit properties, right, one of the kind of basic assumptions you're working with is that these limits exist. They give you numbers, right? If you don't have those limits, you don't have any of these properties. So you can't really do much with that. The third one I can take care of. The third one is fine because I can say, well, that's 5 times the, oh wait, you know what? I can't. Let me fix it. G, let's make that g of x. Okay, then I can write that as 5 times the limit x going to 2 of g of x. And from the graph, it looks like g of x is getting pretty close to 2 as y approaches 2. So I can say, well, that's 5 times 2, and I get a value of 10 for the limit. Now, the reason I didn't tackle 1 right away is there's a small issue with that one that we will address later on, which is, well, the graph doesn't tell me what goes on over here, right? When I let x approach minus 2, I really need to allow x to come at minus 2 from either side, x being bigger than minus 2 or x being smaller than minus 2. I don't know what the x value, or I don't know what the y values are when x is smaller than minus 2. I don't even know if they're defined. Later on, we'll see that we can still talk about situations like this. We can talk about one-sided limits. We can talk about left-hand limits. We can talk about right-hand limits. So if we were just considering only the values bigger than minus 2, if we were talking about these right-handed limits, well, then we could kind of make sense of things because we could say, well, it looks like, you know, as x closes in on minus 2, right, it looks like f of x is getting close to 5. It looks like g of x is getting close to 4, and so if I wanted to calculate the limit of the sum, it would be the sum of the limits, so I would do 5 plus 4. I would get 9. All right, so those are some of the basic properties, and we're going to put those to use in the next few videos and in class. We're going to work through some algebraic examples where we start manipulating limits to get values out.